Matthew, Ivan, welcome.
Thank you.
Thank you.
It's my pleasure.
So this session is rather unusual in that we can hold it in one of two languages. So Ivan is bilingual, and so we were going to switch to Spanish if that is what people would prefer. So what we, I guess, need feedback from is, Angel, do you prefer English or Spanish for this podcast, for this presentation? Okay. Well, Ivan, which one are you more comfortable in? Shall we do it in Spanish anyway?
We could do both, either one. Yeah.
Okay, so let's plan. We were planning on doing in Spanish, so why don't we go ahead and do that? So the recording will be in Spanish, so that will be a boost to, I think, having that on the Shadow the Scientist site.
Mm-hmm.
Claro
Okay.
que sí, estoy de acuerdo. Qué bueno, Iván.
Sí, gracias.
So, Ivan, why don't you start us off?
Yeah. Okay. No sé cómo empezar, pero buenas noches todos. Voy a empezar con esta presentación hablando de qué exactamente vamos a hacer hoy y cuáles partes de astronomía vamos a hablar. Here we go. So, mirando esta foto, ¿qué es lo que vemos en esta foto? Hay muchas estrellas, pero ¿qué específicamente hay interesante aquí?
Bueno, los tamaños de las estrellas son diferentes y hay colores diferentes también.
Sí, hay unas estrellas que aparecen más grandes que otras, como aquí en el centro hay 3, 4 que son muy brillantes y una aquí en el centro que está muy roja. Y eso es lo que queremos analizar y ver por qué están diferentes, por qué son especiales. Para analizar dónde están las estrellas, usamos algo similar a las coordenadas de la Tierra. En la Tierra usamos latitud, longitud y altitud. Es como norte al sur es latitud y longitud es este oeste. Entonces es esta línea acá. Y la altitud, pero sí, esa es más fácil como interpretar porque es arriba y abajo del mar. Y pues referimos a estas coordenadas como las coordenadas terrestriales. Y el cielo tiene algo muy similar, pero ahorita vamos a esperar de hablar de esos. Pero ahorita vamos a hablar del cielo. Tenemos Polaris, la estrella del norte, o the North Star. Y tenemos más estrellas circumpolares que son bien cerca a la estrella del norte. Y esta estrella del norte está al centro del polo norte en la Tierra. Y estas estrellas circumpolares son muy cerca de este polo norte, pero no exactamente. Y tenemos estrellas no circumpolares, entonces son más lejos de ese polo. Y esas estrellas tienen un punto fijo y no realmente no se mueven tanto, pero parece que se mueven durante el día y durante la noche especialmente, porque la Tierra tiene una rotación para el este, or east, to be English. Y por esta rotación parece que las estrellas se mueven cada noche. Y sí, con esta foto acá atrás, vemos que trazan como círculos alrededor de este punto en el medio. Y cualquier persona puede tomar fotos como esta. Esta específicamente fue tomado en Mauna Kea, donde dejaron el obturador del telescopio abierto por algunas horas, mm, no sé cuántas exactamente, pero no fue tan largo. And for those of you that don't know, obturador is the shutter of the telescope. Y como dije, cualquier
Um,
persona con una cámara, ¿cómo se llama?
una pregunta, lo siguiente. ¿Cómo se escribe la palabra que se usa para shutter? ¿Cómo se escribe? Puedes
Oh,
ponerlo en el chat. Es una,
sí,
es una palabra nueva para mí.
sí, no, también para mí era nueva y es diferente que shutter. Pero, ya, y también, como vemos aquí abajo, es el horizonte, es donde el cielo y la tierra se juntan. It's the horizon, where we see the earth and the sky part. Y las coordenadas de la esfera celestial son iguales a las coordenadas de la Tierra. Y como podemos ver aquí en esta foto, tenemos la Tierra y afuera en la atmósfera vemos una esfera celestial donde podemos como encontrar las posiciones de estrellas y otras cosas afuera de nuestro sistema solar. Y son muy similar, pero tienen diferentes nombres. Donde la Tierra tiene latitud y longitud, la esfera celestial tiene declinación y ascensión recta. Y sí, tienen, perdón, tienen puntos muy similares porque lo pusimos que el polo norte de la Tierra está en el mismo punto que el polo norte celestial y por eso son tan iguales. Mucha gente da crédito de la invención del telescopio en 1608 para Hans Lippershey. Y el primer uso de este telescopio para estudiar el cielo fue por Galileo en 1609. Y un año después de esto, en 1610, él construyó otra versión que fue mejor que el original y publicó un libro llamado El Mensajero Estrellado. Nuestros telescopios usan algo que se llama un refractor y eso es básicamente un tubo largo que tiene un lente fijo, un lente objetivo enfrente. Y este lente objetivo que está ahí abajo del tubo colecta luz y lo enfoca a una parte posterior al tubo. Entonces entra aquí y lo fija todo con espejos aquí. Y el ocular es, pa- es un modo, o un instrumento muy importante porque nos deja ver la imagen que el lente objetivo nos deja ver. Y es difícil, muy difícil crear uno de estos lentes, pues uno de esos lentes grandes, porque los colores tienen diferentes modos, porque dependen en el color de la luz. Y esos modos son diferentes porque se pueden doblar o refractar en diferentes modos. Y estos problemas son resueltas usando un telescopio reflectante, donde la luz se mete por acá y este espejo lo avienta para este segundo espejo y ahí sí es como lo podemos ver. Aquí son algunos ejemplos de telescopios, como tenemos este Prime, Newtonian, Cassegrain y Code. Y así podemos ver que la posición pues los espejos pueden cambiar la imagen mucho, como el lens donde nosotros lo vemos, pues, hace muchas cosas para que nosotros lo podemos ver muy diferentes. Y este telescopio que vamos a usar hoy es el Shane Telescope del Observatorio Lick. Y cuando fue construido en 1959, era el segundo más grande del mundo. Y entonces este telescopio es un poco joven, porque no, pues fue creado como, ¿qué es eso? 60 años, hace 60 años. Y adentro tiene un espejo que es 3 metros de ancho y pesa 145 toneladas. Y para que este telescopio funcione correctamente, usamos, tenemos técnicos que lo mantienen. Fue, fue diseñado por ingenieros para ser más fácil y muy eficiente. Y tenemos un programa original que fue creado del Observatorio Lick para para poder ejecutar todos los programas y comandar qué podemos hacer con este telescopio. Y tenemos operadores que lo controlan y usan ese programa para para hacer todo el trabajo que hacemos. Y pues telescopios tienen muchas partes y que llamamos instrumentos. Y sin estos instrumentos son como carros sin motores.
Me
Y
encanta esta descripción que telescopios sin instrumentos son como carros de motores.
Ujú.
Perfecto, me encanta mucho, me encanta mucho.
Bueno, para empezar, el instrumento más simple que podemos usar es el ojo. Y ese es el instrumento que muchos astrónomos usaron al principio cuando no tenían telescopios. Y ya que estamos en el futuro, la sociedad moderna, usamos cámaras y podemos preguntar por qué son mejores usando una cámara que usar un ojo.
Angeli Metzli, por favor, puedes poner sus respuestas en el chat si quieres, o si quieres unmute yourself. Lo siento que no sé cómo decirlo en español, pero si quieres unmute yourself para responder, hágalo, hágalo. Y yo quiero decir que yo creo que los ojos son buenos porque bueno, I mean, hay límites que podemos ver con los ojos,
Ujú.
pero I mean, cuando estamos cerrando cosas, ojalá que es claro y podemos ver los detalles
Ujú.
que nos dan más información sobre el objeto.
Sí. Sí, podemos ver como más claramente con una cámara y a veces con tiempo nuestros ojos no ven como lo mismo. A veces todo se ve más borroso, pero con una cámara la calidad se mantiene.
La calidad es muy importante, sí. Oh, and we have from Angel. is it because we have photo evidence, so we can maybe even have a more clear picture? What do you think, Ivan, Matthew? Yes?
Yeah, I agree. Is there anything Matthew wants to say about it?
A more clear picture, so that even more important is just being able to prove to somebody you saw something amazing, right? They may not believe you if you don't have that evidence. So extraordinary claims require extraordinary evidence, and every scientist wants to have an extraordinary claim.
And something I kind of wanted to bring up was that I guess before they had telescopes or cameras to record all this data, a lot of the astronomers would try their best to remember the stars and what the sky looked like. So using these cameras would, I guess, make a more accurate representation because, of course, memory isn't going to always be accurate. So lo que yo expliqué es que astrónomos antes que tenían cámaras, cuando usaban su ojo, es posible que no se recordaban dónde en el cielo están las estrellas. Entonces, cuando las dibujaban, no son exactamente lo mismo que el cielo o lo que vieron, porque no se van a recordar dónde está una estrella en tantas arriba. Pero hay limitaciones de lo que las imágenes de estrellas nos puede decir. Y pues usando imágenes de estrellas, solo podemos ver los detalles físicos de estas estrellas. Entonces, sí son muy brillantes, muy rojos, muy azules, muy chicas, pero realmente también queremos saber la temperatura, los químicos que están en su atmósfera y de qué realmente qué está adentro o sí, adentro de esas estrellas y cuáles elementos hacen sus atmósferas. So, I don't know where the picture is. Bueno, aquí
Oh no, desapareció. Did it disappear? Desapareció.
I hope not.
Oh no.
It's here on my other laptop that I'm looking at the same presentation through.
Okay. All right. Awesome.
Well, bueno, lo que debemos tener una imagen que enseña luz entrando un pedazo de vidrio y saliendo con un arco iris que tiene todos los diferentes colores. Y los colores son muy importantes a analizar las abundancias químicas de las estrellas, porque analizando estos colores nos dice cuáles aspectos, cuáles químicos tenemos en la atmósfera. Este estudio se llama espectroscopía. Ah, there it is. Ahí está la foto. Bueno, cuando vemos cuando tenemos una estrella como el Sol, manda la luz a la Tierra y esta luz tiene diferentes colores, pero queremos saber cuáles químicas está mandando, cuáles químicas aparecen aquí afuera del Sol. Usando la luz podemos hacer eso y podemos ver las líneas de sodio, las líneas de oxígeno y también carbón. Y aquí es donde están las químicas y estas refieren a un cierto color que podemos ver. Como aquí tenemos hidrógeno, hierro y sodio. Y viendo estas bandas de luz, podemos ver que aquí es donde tenemos la luz de algo bien caliente. Entonces no tenemos químicas que están absorbando cierta luz. Y aquí abajo, las líneas oscuras nos enseñan to- cuáles químicas tenemos y cuánta luz está absorbando. Entonces las que están más oscuras están absorbando más luz. Y así es donde como podemos, sorry. Y así es como podemos determinar cuáles estrellas tienen ciertos químicos. Y aquí es como las analizamos. Como antes, aquí los vimos de arriba para abajo y en estos los vemos en el lado, donde cada vez que baja mucho la línea es el químico absorbando la luz. Entonces, tenemos el wavelength de la luz que está absorbando un cierto número de luz y lo más bajo que está nos dice que está absorbando más de la luz y si está absorbando más de la luz, tenemos más de esa química. Más de nuestro telescopio de esta noche, estamos usando el espectrógrafo KAST de doble canal y este espectrógrafo fue construido en 1992 y necesita mucha gente para operar, sí, para completar sus operaciones y solo trabajar en este. Tenemos técnicos también que lo están manteniendo y otro programa original para que funciona correctamente y hace los diferentes trabajos que queremos hacer. Y tenemos otro equipo de astrónomos que operan este. Y para ver estas estrellas, hay mucha gente que ha trabajado en ser astrónomos solo para ver estas estrellas y la diversidad de mucha gente nos ayuda mucho porque hay ciertas personas que ha hecho mucho trabajo para la astronomía y para traer nuestra tecnología a este nivel que no agarra la atención. Sí, sí, las mujeres han contribuido mucho para astronomía y para tecnología en general. Una es Annie Jump y ella, pues su trabajo era para analizar espectra y hizo mucho trabajo, especialmente para espectra. Y mujeres, como dije, han hecho mucho trabajo en en los 1900s siendo computadoras. Entonces, estas son las computadoras originales, donde ahora tenemos computadoras pues, digitales que hacen matemáticas y programas para hacer todo nuestro trabajo. Pero antes había un equipo de mujeres que se llamaban las computadoras y ellas hicieron toda la matemática para astronomía, especialmente como también hay una película, mm, eh, no sé, no me recuerdo qué se llama, but
Hidden
there's a,
Figures? Como Hidden Figures?
yeah, se llama Hidden Figures. Es una película muy buena. Luego cada 2 años, creo. So it's always good to remember it. I like it.
Me encanta también, me encanta mucho. Es muy inspirando.
Ujú. Bueno, esa es una de estas mujeres, Annie Jump. Ella creó un esquema de clasificación para estas estrellas y eso es, y hizo esto cuando estaba analizando las espectras y nadie, y este es muy especial porque todos antes de este punto pensaron que las estrellas fueron todo lo mismo, pero ella cuando las clasificó enseñó que hay diferentes tipos y diferentes niveles de especialidad de estas estrellas. Y otra mujer, Antonia Mauri, ella pensó, ¿qué pasa si las clasificamos estas estrellas y esta clasificación y hacemos otro, donde las clasificamos por color? Y ese es la sistema moderna, es donde las estrellas son clasificadas por lo más azul, aquí en las estrellas de O, y las más rojas son acá en el lugar M. Y mucha gente pensaron que la composición de cada clasificación fue diferente, donde las estrellas de A tenían más hidrógeno y pues más líneas de hidrógeno, cuando las líneas de K y M no tenían pues casi nada de hidrógeno en su atmósfera. Y hay algunas estrellas en esta clasificación M que tienen mucho sodio, entonces tienen las líneas más oscuras en el wavelength de sodio. Y aquí tenemos Magnat Saha. Y él pensó de la teoría de ionización termal de átomos. Y este hombre viene de India. Entonces el otro lado del mundo, y donde él pensó que las diferentes temperaturas de las estrellas es lo que está causando estas líneas diferentes, estas diferentes abundancias de químicas. Es- y aquí tenemos Cecilia Payne Gaposchkin, creo que eso es como, así se dice bien, pero era la primera doctora de astronomía en Harvard y Radcliffe. Y ella fue lo que conectó todos estos diferentes tipos de información, donde tenemos las diferentes clasificaciones con la temperatura y ella lo conectó todo. Y, bueno, aquí podemos ver que las estrellas perdón, tienen su propio nombre de cada clasificación y casi todas las estrellas en el cielo tienen los mismos químicas adentro. A ver, one second, can you hear that? Okay, cool.
No, sure did not.
Oh, sorry, my housemate's cooking. That's why.
Oh, okay, yeah, all good, no worries. Didn't hear anything,
Yeah,
didn't hear
okay.
anything, just you. Ivan.
Okay. Perdón, ¿qué estaba diciendo? Oh, todas las estrellas están hechas de los mismos químicos, pero tienen diferentes niveles de abundancia de estos químicos. Y las estrellas usualmente tienen mucho hidrógeno y helium, creo que es helio, en español, pero tienen poco abundancias de carbono, nitrógeno, oxígeno y los otros elementos. Y es el tamaño de la temperatura de la estrella que cambia cómo el espectro se ve. Y la temperatura es basado mucho en el tamaño de la estrella. Entonces, las estrellas más grandes van a ser, es muy diferente que las estrellas más chicos en términos de temperatura. Como las estrellas acá arriba, en el nivel de O, van a ser mucho más grande y mucho más caliente que las estrellas acá abajo en el nivel de M. Y pues, así es como vemos las temperaturas. Con las estrellas de O son más calientes de 25.000 Kelvin. Y aquí en el medio tenemos de F, tenemos estrellas que son 6.000 y 7.500 Kelvin. Yes.
Bueno, es verdad que las estrellas de clasificación O son las más grandes y más calientes de todos.
Sí, sí es cierto. Y
Ah,
esta temperatura es la razón que son tan grandes, porque si son tan calientes van a ser muy grandes. ¿Sí? Y ya, este es pues, el proyecto que yo estoy haciendo, es clasificando las estrellas de carbono, porque son más extrañas que estrellas normales, porque estrellas de carbono tienen más carbono en su atmósfera que oxígeno. Y sabemos esto porque estamos buscando para la molécula C2. Y el espectro de la estrella cambia dramáticamente por esta imbalancia de carbono y oxígeno. Y es muy fácil detectar estas estrellas cuando estás buscando para estas moléculas de C2. Sí, en este proyecto estamos buscando las estrellas de carbono y prediciendo cuáles estrellas son estrellas de carbono y cuáles no son. Y usando los espectrales de la infrarroja, donde no hay bandas de CO2. Y estos modelos predicen que hay más carbono que oxígeno. Mm, Eso creo que vamos a preguntar a Matthew, ver si él está listo. Matthew, how's everything going on your end?
That's cloudy, cloudy. So, are you near the end of your presentation?
Oh yeah, I'm at the end, yeah.
So, what I could do is share the different screens, and you could talk a little bit about, or I could talk and you could translate about a little bit what you see. So, I'll start with, if I can figure out, let's see, sharing one of these desktops, the weather. So I think you can cover the weather pretty well.
Yeah, so lo que estamos viendo aquí son dos programas que nos enseñan la clima del cielo. Y aquí en estas cuatro fotos vemos que está bien nublado, entonces va a ser más difícil de ver las estrellas. Y también acá en la derecha vemos la temperatura, que tan húmedo es la velocidad del aire, la dirección del aire y la precipitación del cielo. So, aquí en la derecha vemos que nos está diciendo que es muy nublado y en vez de tener que salir y ver cuáles niveles, aquí tenemos toda la información lista para nosotros y nos dice si podemos ver las estrellas esta noche o si tenemos que esperar más tiempo. So if it's looking a bit cloudy, it's not a very good sign, but hopefully it'll clear up, right?
The prediction is 100% chance for rain all night long.
Mm.
But sometimes they get it wrong. So I will stay here until 3 o'clock in the morning, probably, and just to make sure. Because otherwise, if I miss tonight, then the chance to get the stars that are available overhead at the beginning of the night, I'll have to wait 9 months before I can try again. So even if I get a little bit of time, I will try to use that time.
Lo que Matthew nos está diciendo ahora es, si vemos el nivel de humedad, vemos que hay casi 100% posibilidad que va a llover esta noche, pero también algunas veces no es correcto y no va a llover, entonces podemos usar el telescopio. Y esta noche tenemos unas estrellas que no tenemos tanto tiempo para verlos, porque si no los podemos ver esta noche, entonces Matthew va a cualquier persona va a tener que esperar 9 meses para verlos otra vez. Entonces, ojalá que sí lo podemos ver o que las nubes se mueven y podemos ver por lo menos una hora. Yeah. Yes.
Yay,
Sí.
Ivan. Yes, you need this data to graduate this year. That's a very important and very, very, very important reason.
So, Ivan, did you talk about the fact that this is your project?
Only a little bit. I said why it was important and whatnot.
So why don't you talk a little bit about what it means to have a project? You know, what the purpose of this project, what a senior thesis is, and then what you did earlier in January to disseminate the results.
Yeah. Las estrellas que vamos a estar viendo esta noche, o ojalá estar viendo esta noche, son muy importantes para el proyecto que yo estoy haciendo de estrellas de carbono. Entonces, ojalá que sí los podemos ver y no tener que esperar 9 meses, porque yo estoy escribiendo mi senior thesis o un papel de información y datos para poder graduarme este año. Entonces es muy importante que suerte está con nosotros. Yeah. And lo que yo he estado haciendo es agarrar las espectras de estas estrellas que podemos ver y analizarlos, ver todo el carbón y todo el oxígeno, especialmente esos dos, pero también veo como el sodio y el hierro y los metales que consideramos más pesados que oxígeno y carbono. Y usando estos datos, puedo decir si esa estrella sí es una estrella de carbono o si no es posiblemente. Y este enero yo presenté, sí, es enero, pero hace 1 o 2 semanas yo presenté pues, mi proyecto o parte, porque todavía no estoy terminado, pero presenté lo que yo he estado haciendo ahí en New Orleans, en una convención que se llama la Sociedad Americana de Astronomía. Y ahí pues, había muchas organizaciones hablando de lo que ellos están haciendo y también muchos estudiantes como yo, muchos graduate students que también están presentando pues, el trabajo que ellos han estado haciendo por muchos años para aquellos que agarran su maestría y mover para agarrar su PhD.
Great. I guess I could keep sharing the screen for different areas. So this is the red side of the detector, and this is a flat field lamp, so I can see how the instrument behaves from pixel to pixel. And I have an intensity plot, and I can start an exposure. Whoops, except there's nothing on at the moment.
En la presentación que yo mencioné que hay 2 canales en este telescopio y este canal es el canal rojo, donde podemos ver las líneas de oxígeno más claramente. Y aquí en el medio izquierda tenemos arriba el azul, pues se ve más morado, pero es la parte de la espectra más azul. Y ahí abajo tenemos la parte más roja. Y lo que él está haciendo es tomando algunas fotos solo para hacer un baseline o un nivel para empezar y comparar con las espectrales de las estrellas que estamos viendo.
Perfect. Boy, you're doing great, Ivan. You're really doing great. Okay, so I'm going to, this is what the taking exposure looks like. I'm going to take this one off and change it to wavelength calibration. So we have a bunch of lamps that are on an argon, a neon, a helium, cadmium plus mercury, Hg is mercury, mercury plus argon, and a neon lamp. And I've turned them all on. And if I can remember the exposure time, should be 20 seconds.
Y lo que Matthew está haciendo ahora, podemos ver a la ventana de la programa ahí en la derecha, la gris. Está prendiendo ciertas lámparas que tienen diferentes elementos adentro de ellos y está tomando las fotos usando las lámparas y el telescopio, y eso nos enseña esta noche. Y, y estamos viendo algo. Está durando un poco tiempo, pero vamos a poder ver las líneas de absorción de las lámparas que hemos prendido.
So this is wavelength and direction. So each of these, if I wanted to know the fingerprint of an element, that is the wavelength that it produces light at. And each element has a unique fingerprint. And so I've turned on a fingerprinting machine, essentially the spectrograph. and with a bunch of different fingerprints built in. So argon, neon, and this is the resulting spectrum. So each of these is a color of light coming out from one of those elements. So some of those make up fancy beer signs in bars or other lights.
Similar a la presentación, podemos ver una representación más real aquí en la pantalla. Donde el programa nos está enseñando las diferentes líneas y lo más grande y oscuros que son. Nos dice de cuáles elementos podemos ver más. Y es difícil de hacer, pero en el arriba para abajo podemos ver el wavelength de los elementos y eso es lo que nos dice cuáles elementos exactamente, porque sin este axis no podemos saber cuáles elementos estamos viendo, pero como sabemos que los elementos tienen ciertos wavelengths, es más fácil para entender lo que estamos viendo y cuáles químicas están en la atmósfera.
So this is the blue chip,
Mhm.
like you had said, the blue side. And this is what the flat field looks like. And here you can see little specks of dirt that came from this very old detector. And so to be able to tell if the spectrum is detecting an absorption or emission or what, we have to know the difference. So we have to take a way to calibrate those out.
Y lo que estamos viendo aquí es el otro canal del telescopio. Este lo llamamos el azul. Y todos es- no sé cómo decirlo, pero los puntitos oscuros es agua en el telescopio y eso es lo que no queremos ver tanto. You said that was a dew, correct? Or am I thinking of something else?
No, it can be. So it can be caused by a lot of different things. Sometimes dust, sometimes dew, sometimes various things that cause the little drops.
Mhm.
Sometimes they're just little dust particles that get stuck on
Mhm.
the detector.
Yeah. So, lo que estamos viendo aquí, los puntitos puede ser un poco de tierra que está encima del detector y que está agarrando el detector, o también puede ser agua que por las nubes que están afuera.
So I'm taking a new arc spectrum, the same lamps as before, but now instead of being in the red side, it's the blue side. So the distribution of lines, which will be instead of it's rotated, the detector is rotated 90 degrees. So instead of having lines this way, it'll be this way. And so now wavelength is in this direction instead of the other direction.
Y usando este canal, el canal azul, estamos haciendo la misma cosa que hicimos con el canal rojo, pero lo movemos el detector 90 grados para verlo en diferente modo. Entonces aquí podemos ver una selección diferente de wavelength y ver diferentes elementos, pero todavía estamos usando las lámparas que usamos para el canal rojo.
Bueno, Iván, tengo una pregunta.
Ujú.
Bueno, ¿tienes que hacer algo diferente cuando cuando ustedes están usando las lámparas rojos y el azul, tienes que hacer algo diferente y es el proceso casi la misma cosa.
El proceso es muy similar y solo es cuando estamos analizando las espectras donde hacemos algo diferente porque analizamos los modelos que, como en mi proyecto, vemos el modelo de las espectras del lado del canal azul primero, las ajustamos y regresamos a la espectra roja, cambiamos diferentes cosas y vemos cómo esos cambios afecta el canal rojo y ver si y hacer esos cambios del rojo otra vez al azul para ver que todo todavía está bien, que los elementos, las abundancias no son bien extraños. Entonces es mucho ir y regreso del trabajo.
So, Ivan, what is the word for molecules?
Ah, moléculas.
Molecules.
You make
Okay.
sure that.
I wasn't sure if you were saying the word molecules or not, and I wasn't. Since I don't know the word, I couldn't know to listen for it.
Yeah.
I don't know the
I,
word either, Matthew. Yo sabía esta palabra también es algo nueva.
So I think the last screen that we have is the one with targets. And this is just, it's kind of boring at the moment because at the moment, there's nothing here. This would be the field that allows us to see if there were the star that we want to look at is visible. And since we can't even open the telescope, there's nothing to look at. And this is our list of targets that we want to do it tonight. The name of the target, and then the different coordinates, right ascension, declination, and then how bright it is.
Lo que estamos viendo en esta pantalla, aquí en la izquierda, usualmente es un campo para ver si la estrella que queremos ver está en nuestra vista. Entonces lo movemos para ver si la estrella que queremos ver está en el centro y lo podemos analizar bien. Pero como no tenemos el telescopio abierto o no, para que no se meta mucha agua, lo tenemos cerrado. Entonces no hay nada aquí en la izquierda. Y esta lista aquí abajo con todos los números son las diferentes estrellas que queremos ver y queremos analizar esta noche. O pues en general, porque hay tantas estrellas que no es algo que podemos hacer en 12 horas, es algo que toma muchas noches. Chemica?
Sí, gracias, Iván y Matthew. ¿Cómo ustedes deciden en cuáles estrellas observar?
Sí. Solo para decidir cuáles estrellas queremos observar, ao- ahora pues, por ahora estamos viendo una lista que ya otra gente ya han observado y queremos asegurar que son claro y que son lo mejor calidad que pueden estar. Entonces estamos viendo las, las espectras y viendo como si hay mucho ruido. Y cuando digo ruido es, es cuando hay diferentes moléculas en la foto que tenemos. Y cuando hay muchas moléculas que no queremos ver, hace que las líneas se mueven muy extrañas y queremos que las fotos que tomamos no sean así. Entonces tomamos nuevas fotos y eso es lo que estamos haciendo. Estamos tomando nuevas fotos donde las líneas están más planas y podemos ver más de los elementos y las líneas de absorción más claro. Y ya.
Okay, so when I'm observing at night, instead of just looking at one of those, I actually look at all of them all at once with like this. So this is what my nighttime looks like, is all of those screens all at once. And so I'm watching and paying attention all night long. But it's pretty easy when you break it down into little pieces.
Ujú. Bueno, cuando Matthew está observando ahí en el telescopio, hay muchas cosas que tiene que controlar y que tiene fijar, que se tiene que fijar. Entonces, para hacer más que una cosa y ver más que una estrella, tiene una pantalla grande donde puede ver las diferentes cosas, como ahí en la izquierda arriba tenemos la, el canal azul y ahí abajo de eso tenemos el canal rojo. La derecha de eso vemos la clima y arriba vemos las estrellas que quiere ver. Y es muchas cosas que tiene que fijar y asegurar que se está manteniendo un ojo y pues con una pantalla grande o haciéndolo en cuatro pantallas más chicas y organizándola pues, con lo que lo que cosas que controlan ciertas cosas, es más fácil de entender lo que está pasando.
So it still looks, the weather is terrible. It's 99% humidity and it says foggy outside. And normally there would be a telescope right here that you would see from in the distance, but you see nothing except for this strange glowing light, which might be a car driving in the fog, but I'm not sure.
Por ahora estamos viendo la clima y como dijimos que va a ser bien nublado, en esa foto ahí abajo, sí es una cámara que nos enseña lo que está afuera en tiempo real y lo que debemos de ver es un telescopio grande, pero está tan nublado que no lo podemos ver. Y esa luz puede ser un carro que está manejando al telescopio o en las montañas, pero no se puede ver porque es tan nublado.
So this might be a good chance for people to ask questions, of me or Ivan, about how we got here, what we do, what we like, what we don't like, any of those types of questions. So are there any questions you'd like to ask? Maybe I should stop sharing so you can see the chat.
Yes, Metzel and Hennifer, questions.
It's great. I was looking for a way to transition to that. Lo que estamos haciendo ahora estamos viendo si alguien tiene unas preguntas para nosotros en lo que nosotros estamos haciendo en nuestro trabajo, en mi proyecto y pues cómo yo estoy haciendo en universidad, cómo yo decidí ser un astrónomo y cualquier pregunta que ustedes quieren, o ustedes tienen, perdón. Como yo empecé en la escuela de Santa Cruz, como yo entré pensando que iba a estar diseñando videojuegos y rápidamente noté que no me interesó tanto. Entonces yo fui a la ingeniería eléctrica y durante eso tomé algunas clases de física y eso me interesó más. Entonces yo haciendo, estoy haciendo la maestría de física, pero durante eso tomé unas clases de astronomía porque están conectadas muy cercas y por eso aquí estoy haciendo astronomía.
Yeah, so what does Matthew specialize in? What is the job you do? What's the job you do called, Matthew? You're the deputy director of Lick Observatory, but what does that actually entail? What does that mean? What do you do on a daily basis?
So let's make sure if I answer a long question, does everyone understand English, or should Ivan translate my answer? So I think we don't know what the preference is for.
Okay, so Metzil entiende los dos. Gracias, qué bueno.
And
Understands both English and Spanish. Jennifer, ¿cuál idioma prefieres? Yes. Okay. So I think that's yes to both English and Spanish. So yes, please. Good with
okay,
both. Excellent. Thank you so much for that feedback, Jennifer.
that
And
just means Ivan doesn't have to work quite so hard to translate everything I say. That's good. So I am a PhD astronomer, and so I actually went to grad school in Santa Cruz, and then went on to work at other observatories. So I worked overseas in Chile, and worked for the European Southern Observatory. So I worked with Germans and Italians and French and Dutch and of course Chileans, and to help people learn how to use a telescope. And then I went from there to another observatory, one in Texas called McDonald Observatory. And there I helped build a gigantic telescope and put new instruments on it. And so this job here in California is the deputy director for University of California Observatory. So we have Lick Observatory and the Keck telescope out in Hawaii. And California is a partner, University of California is a partner in that telescope. And so I help make sure all the astronomers from all of the UC campuses, UCLA, from Berkeley, from Riverside, they all get access to those telescopes, know how to use them, and if there are problems, if they want better instruments in the future, what their priorities are, even for education. So they want to bring classes up. If they want to take an undergraduate class up, I help make sure that that works. And La Noche, so I give approval for the La Noche group to go up to Lick Observatory. So, so my job is administrative, largely, but I still get to do some research. And because I have a lot of administration stuff to do, I teach students how to do research, and then they do all the hard and fun research side, and they come and tell me what they're discovering, and I help them understand what they're discovering. So I hope that was somewhat clear.
sí, creo que sí. Qué increíble. Qué
So I wish so 24 years ago, when I was living in Chile, I knew no Spanish. I only knew English and German. And then I learned some Spanish to survive living in Chile. And then I moved out and didn't use it for another 20 years. And so it got very, very rusty. So I can hear a little bit and understand a little bit, but I certainly If I try to remember a word, there's about a 30% chance it's going to come out in the right language. It could come out in German. So it's a little embarrassing to speak half German, half Spanish.
Well,
Yes, I agree. I agree with Metzley. I understand. Very, very interesting. Yes, we gotcha. We appreciate you sharing with us, and whichever language works for you, Matthew.
So any other questions? They can be questions about astronomy in the news. It can be questions about engineering, about computer programming, about getting into college. It could be any kind of question you'd like.
Well, I'll start off while maybe Metzl and Jennifer are thinking about questions. Um, Recently I read and also heard in one of my many astronomy podcasts that I listened to that they were talking about planetary nebulae and how our star and just our sun would we thought because of its low mass. I know we haven't talked about masses of stars and and the kind of end that they can have, a planetary nebula or black holes or different things depending on the mass. But I read that our star, even though it's at one solar masses and we compare other stars to our own local star based on that, but that our star would may perhaps not to go through the planetary nebula stage. And I had the honor of speaking to Dr. Steve Howell, who was and is the PI, the principal investigator of the Kepler mission looking at exoplanets at NASA. Had a fantastic conversation with him at AAS, as Ivan was saying. I hate that I missed you, Ivan. Raja and I were both at the American Astronomical Association meeting in New Orleans recently, last week and a half ago. And I hate that I missed you, but one of the things that Steve Howell and I talked about was this idea, what not idea, but this determination about planetary nebula. I guess there's new data, maybe that seeing the planetary nebula in the optical, where we're looking for is that expansion of gas and dust, and see that and identify as a planetary nebula. But in the infrared or other wavelengths, if you aren't seeing it, um, they're in the same wavelength, maybe that it's interpreted as something different. Could you maybe speak to that and maybe just explain maybe the stellar evolution in a quick nutshell, Matthew? That ain't quick. I know. I'm sorry. But maybe at the asymptotic branch, and then what it means, planetary nebula, and maybe your insights on this new insights that perhaps seeing planetary nebula in the optical isn't necessarily all there is to determining whether stars are going to create like our own star, which is a G2V type star. Maybe there's a little bit more to it. What do you think, Matthew and Ivan?
So a planetary so when big stars die, they die spectacularly. So they run out of gas and inside the middle of the star, and the star collapses down on itself, and it either collapses into a black hole or it does a bounce and the material comes off in a spectacular explosion. And we call that a supernova. And so that's the fate of gigantic stars. And the fate of stars that are a few times bigger than our sun, so maybe only 50% bigger or twice as big, they run out of fuel in their center, the hydrogen into helium, burning of fuel. And then the center part starts to just cool off into a gigantic marble, very hard thing in the center. And the outer parts sort of drift away very gently. And if the star is spinning, then sometimes it can get a different shape, and it can be really stunningly beautiful, like these. So those are images of planetary nebulae. And so you can sort of see the gas cloud blowing off. And in some of these, you can see a little hot thing right in the center, a little dot. And that hot marble is making the gas glow. And of course, we know about it because you can look through a telescope and see with your own eye. You can see the optical image, but that may not be quite what it looks like if you were to look in the X-ray, or if you were going to look in the infrared, you might see something different. So in astronomy, every time we open a door to a different part of the universe, a way of looking at the universe, it's like a perspective. And so Jamaica's perspective is different than my perspective. And so if we come into a room and we share what we see, we get a better feel for what is actually in the room. I might come in the room and I see all the dollar bills stacked up on my table. And Jamaica comes in and sees, something else, sees the dog sitting in the corner. And so getting the different perspective, you get a better feel for what my office might actually look like, whether it's dollar bills stacked up over there or the dog sitting in the corner. So in astronomy, there are different ways of looking at the universe. And one of those is with optical telescopes. You can take images, you can do spectroscopy, you can look in the ultraviolet, you can look in the X-ray, just like you have X-ray machines in hospitals that can look at your body in a different way. X-ray telescopes look at the universe in a different way. James Webb Telescope is an infrared telescope, and it looks at the universe in a different way than Hubble Space Telescope did, and the optical telescopes on the ground do. So it gets a different perspective on the universe. And I think that new perspective is letting us learn more about the ultimate fate of stars like our sun. We only know because it takes our sun is 5 billion years old. It's middle-aged. It may take another 4 or 5 billion years for it to get to the point where it starts to run out of hydrogen in its center. So it's hard to find stars like our sun who are 9 billion years old and are ending their life. So it's difficult to know what the fate of our sun is because we can't go out and easily find stars that are the same mass as our star, the same composition as our star, but are twice as old. So that's where this new visions of trying to find other stars in our galaxy or nearby galaxies that might allow us to gain more insight to our own sun. All right, so I can...
Thank you so much, Matthew. Yes, yes. And now we have a question from Metzli. Metzli, please let me know if I am mispronouncing your name. Please accept my apologies if so. And so the question is, may I get your perspective on this question? Does light pollution affect seeing stars?
It absolutely affects our ability to see stars. So this observatory, Lick Observatory, used to be at a very dark location above a tiny little town of San Jose. And but that was in 1888, back when there was the gunfight at the OK Corral in Arizona. So that's how long ago it was back when there were gunfights happening at, westerns. So, but because you can't move an observatory, all you can do is, if you're going to build a new telescope, decide whether you need a darker site or not. So some of the best observatories in the world are at very dark locations like Antarctica or the top of Mauna Kea in Hawaii. And that's where Jamaica is, right?
Yes, that's correct. That's correct. So Mauna Kea is over here for me, and yes, I can. From my home is blocking it, but if I were to go just a little bit down the road, I can see the entirety of Mauna Kea, and I can see the observatories on the eastern ridge. It is quite incredible, absolutely, including the Keck observatories, which the University of California has, just in general, all of the UC campuses have access to.
Great. So that means that this observatory that I'm working on, Lick Observatory, it can't do some of the things that it used to do because of the bright lights of the city. So if you want to look at the very faintest stars, the sky gets bright because the lights from the town trickle up to the sky and then scatter back down. And so it makes the sky brighter. And so you can't see the faintest stars. But if you're working on brighter stars, then the impact is far less. In fact, it's so much lower that you can almost ignore it. So it does impact us, and it impacts us in a way that we can no longer do work at Lick Observatory on the very faintest objects. And we have to leave that for other observatories like the Keck telescopes in Mauna Kea, or at observatories in McDonald Observatory in dark West Texas, where there aren't very many towns, or JWST. So JWST has a very dark site because it is in orbit around the sun, not even in orbit around the Earth. It's in orbit around the sun. And so it's very, very dark there, and it can see incredibly faint things. So it's great if we could try to make the site. For years, for decades, we've tried to work with the city of San Jose and Gilroy and Watsonville to have fewer lights pointed upwards, and also changing the color of the light, changing it from just broad white light to like a sodium light, where it all comes out in only one wavelength. And then we're only destroying our vision of the sky at one wavelength. But now people have stopped using sodium lights and have gone back to LEDs because they're less expensive. And so LEDs produce a lot of light over a broad color. And so we're back to the same problem again. So it would be great if everyone had a dark site, but we're not going to, it's people's safety over astronomy. So we can go and do some of the work at other observatories. Jamaica?
Okay. Wow. I'm trying to block out the light from
Yes,
this
I see that.
fun behind me, y'all. I'm so sorry. This is actually my background. I'm at home. Okay. Wow. You said some observatories are no longer, I mean, some areas are no longer using the sodium vapor lights, and they've switched back to LEDs. Now, what's the I mean, but the sodium vapor lights is so much easier to subtract that noise from the spectra. It's not convenient for astronomers. Why have they made that change?
They make that change because LED lights are cheaper, and they are people don't like the way they look under a sodium vapor lamp. If you go out to under those orange lights that are street lights out there, sometimes they have kind of a weird color for your skin, and so people don't like that. They'd rather have a light that is a full rainbow of colors so that they can see the difference between red and blue, and they can see how they look. And so it's kind of a preference of aesthetics and also monetary. So, but it affects, bright lights affect people's health. The effects, migrating birds, insects, the monarch butterflies, which travel from Mexico up to Canada over generations. They overwinter in Santa Cruz. So those are, when they try to fly at night, they get very confused by bright lights. And so if the lights are less pointed up, then that's better for migrating birds and animals. And if the lights are less intense, it's better for sea creatures who, look for a full moon to come up onto the beach to spawn. If they see a bright light, then they're like, oh, well, is that the full moon? Am I coming up at the right time? Where is everybody? I'm up here. I'm waiting for everybody else to show up. So it really affects a lot of the animal kingdom, and humans are animals, and we are affected as well. And there are some studies that say that very bright lights at night are bad for you. That's why some computer or phones have a dimming effect, that they dim at night. It's for your health.
Incredible. Thank you for that. Um, and you mentioned James Webb, JWST. Could you maybe talk about the Lagrange points and L2 in particular?
Okay. So the there's a lot to go through there. So to get away from the Earth, and to get away from the brightness of the Earth, and the Earth is bright because the sun shines on the planet and it reflects off of the planet. And so there are two things to avoid for Hubble. Hubble can't point at the Earth, and Hubble can't point at the sun, and Hubble can't point at the moon. So it's constantly trying to figure out, what part of the sky am I going to look at and plan on. And so it's limited as far as what it can look at. If you put something further away from the Earth and the moon, then you have much more of the sky you can choose from to select. So to get something outside of the Earth's orbit, but someplace stable, they've chosen a very special location. So there's the sun, and then there's the Earth and the moon. They're kind of here together close. And there are special locations. One of them is sort of a part way between the two. And then one's here, and then one's here, that are stable. So that means if you put something there, it doesn't fall towards the sun, and it doesn't fall towards the Earth if it's going fast enough. So it has to stay in the orbit. So as the Earth moon kind of goes around the sun, there's this point here called the Lagrange point that also can stay in a stable orbit away from the Earth and the moon and not fall towards the sun. And it's because it's moving quickly, but it's also at this special location near the Earth's orbit. Not too near, though. It's like maybe a quarter of the way around the orbit. So anyway, so that's where the James Webb Space Telescope is, which is a bold decision, because when they put in the Hubble telescope into orbit around the Earth, they messed up the optics. And so they went up and fixed the optics on the Hubble telescope. And then when the instruments started to get old, they took the shuttle up there with a new instrument and pulled out an old instrument and plugged in a new one. But that's because it's in orbit around the Earth. But James Webb is way away from the Earth in this Lagrange point. And so really, if something goes wrong with the James Webb telescope, that's it. There's no going out there and fixing it. So the engineers really had to make sure that they got it right and had redundant backup systems, and the computer programmers, if the antenna doesn't point to the Earth and can't hear anything, they better have a backup plan for, oh, well, we better hunt for the Earth and, get our signal, because if it's collecting data and can't send it down to us, then it's not going to be a very good space telescope. So all of those people 2 years ago, 2 years ago or 3 years ago, when it launched, 2 years ago, when it launched on right around Christmas, all of those people were all holding their breath, watching that rocket go up, saying, please don't blow up, please don't blow up, please don't blow up. And then it got into orbit and then launched. And then a couple of months later, they were holding their breath, saying, when the whole telescope kind of had to unfurl from its little package, it kind of unfurled like a flower, maybe a sunflower. And so they were all holding their breath, going, oh, please unfurl, please unfurl, please, will the motors turn on, and everything worked perfectly. And that's why, in fact, it worked so well that it was supposed to be just a few years that it was going to operate, and then it was going to run out of fuel. But they thought, well, maybe if it works efficiently, it could last longer. And it worked just about as efficiently as it possibly could. And so it will last maybe more than a decade if something horrible doesn't happen to it. That's right.
Brilliant. Thank you so much, Matthew. Is there any synergies or collaborations that you have with scientists using JWST or any of, or even any other observatories, whether they're space telescopes or ground-based telescopes that you work with in order to enhance your research? That's for you and Ivan.
So the work that I do is most directly from ground-based telescopes. But so the nearest galaxy to us is the Milky Way galaxy, the one we're in. And so I study the Milky Way galaxy in great detail, star by star. But I'm really interested to know how you can change what we're learning about, like studying a forest by studying trees in the forest, versus what you get from if you were to look at a forest from a satellite and you're only getting a big picture of the forest. Can you learn something else? So James Webb is allowing us to see early baby galaxies forming that are 10, 12 billion years old. And we're getting to see what those look like at early times, because we can only guess what our Milky Way galaxy looked like when it was 1 billion years old or 2 billion years old. We can make models and simulate what that might look like, but we actually don't know what it looks like. And so that's the connection that I pay attention to, is translating what we're seeing in the local universe today versus what we're seeing in the very young universe with James Webb. So Ivan, have you been watching the images and information you get from James Webb? Was there anything that you've seen that was exciting to you?
I have not been keeping up with it, I will be honest. But by the sounds of it, I want to now. It sounds like a lot of unknown that we can find. And I don't know, that's very interesting. You get to see a younger part of just not in our solar system or around us.
Absolutely, Ivan. I would yeah, definitely agree with you. It's been wonderful to speak with, you know, NASA staff who are on as a part of just NASA in general, but also those who are part of different missions to see how they are able to advance astronomy and our understanding with new technologies. And they certainly are very welcoming and excited to welcome people to start to follow the different missions that are happening, especially those of you who are scientists actively doing research in this area, as you, Ivan and Matthew, are. Absolutely.
So one of the things that's also a synergy is what Ivan is doing um, with a star and modeling the star spectrum. So that's a hot body in the center with gases around it. And as the hot photons leak out of the center of the star, they get absorbed by all the molecules and the atoms that are in the atmosphere of that star. And so he gets to see these molecules. Well, people with JWST are now using the same techniques, but not on stars, but on planets going around other stars. So they can go and look at a star, a planet that may be 2 or 3 times the size of Jupiter, or maybe 2 or 3 times the size of Neptune, and see what it's made out of, what molecules are in its atmosphere. And unfortunately, right now with our technology, we can't find anything that's Earth-like and take a spectrum to look at the Earth. But if you took a spectrum of the Earth from the outside, you'd see nitrogen, you'd see carbon dioxide, you'd see oxygen in our atmosphere. James Webb has started taking spectra of these other planets, and they're finding carbon dioxide, water, and these other molecules. And so they're starting to see atmospheres of other planets. And that's pretty exciting. And it's the same techniques that we're using, that Ivan is using for the stars, but it's applied in a different way. And then they have to get fancy because stars don't have clouds. So what does it mean for an atmosphere model to have a cloud? And so they have to get fancier models than the ones that Ivan and I are using.
Amazing. Amazing. Matthew, Iman. Iman, did you want to add anything before I go to a question from, this is a question, yes, a question from, I believe it's Angel. Anything you'd like to add, Iman?
I was just gonna add, I'm interested to see how, I guess, their model atmospheres would look as compared to the ones that we've taken a look at.
And so as scientists, as astronomers, or even just regular people, but certainly as astronomers, is there a way to access the data release, the data that have been released? I know I assume that there's an embargo period where once the data comes in, the scientists who submitted that proposal have a certain amount of time to look at that data just themselves before the data overall is released to the community, to the public, for anyone. Have you made use of those kind of data releases?
I have not. So the type of work that I do is based largely on ground-based telescopes on nearby stars. And JWST, it would be kind of a waste to use this. It's like using a Ferrari or a Formula One car to go get groceries. You don't use your Formula One car to go get groceries. You use your bicycle to go get groceries. So So James Webb is this very fancy, billions of dollars telescope. So you use it to answer the questions about what are planets going around other stars made out of? What are the first black holes that are forming? What were the first galaxies look like? When did they form? Some of those different questions. And then we take all of these different questions in astronomy and put them together into a picture of how our universe operates. So it takes, you can't take your Formula One everywhere. Sometimes you need a bicycle to do some things. So
Absolutely, Matthew. Fantastic point. Fantastic point. Okay, so I guess we can switch to our question here from Angel. Could we use older galaxies to maybe estimate how our galaxy might look in the future? Ivan, Matthew.
So people make models. Actually, all astronomers, all scientists make models. And so that's how we try to interpret the world. And the models are never perfect, right? If it was, we would be building the universe. And so we just build a simulation or a model. So a model of a person might look like a stick figure. A model of the universe is a stick figure view of the universe. And so we have models of what the Milky Way, how the Milky Way may have formed. And we have ideas about how many little galaxies come together like building blocks to form the Milky Way like if you were building a house, how many little building blocks do you have to build? Do you bring them as big blocks or as little blocks? And so you bring them all together. And so we have a model of what that looks like, and we have ones that seem to match what the Milky Way looks like now. And so you're like, okay, then that must be a good model. And then we go back and we look in the past and say, how well does this model predict based on what James Webb is seeing of very young galaxies? Does that model hold up? And the models are not doing very well in predicting how many black holes there should be and how much rotation and gas is coming in. And so we may have to change the model a little bit. But all of these models, the great part about them is they evolve with time. So you're watching a galaxy being put together brick by brick, and then you can say, okay, we got to today and it matches today. What happens in 1 billion years? What happens in 5 billion years? What happens in 100 billion years to our Milky Way? And we can use those models to predict what it might look like. Unfortunately, it's like playing with stick figures, right? So the further you get away in time from today, the worse the model is going to predict. But our idea of what the universe might look like is gas turns into stars. And then stars either explode, massive stars explode, and the gas comes out, and then it becomes the cycle of stellar life. But little stars, they turn into little hard cue balls, right? At the center of those planetary nebula, there was a little hot cue ball at the center. And then that gas can never be recycled again. And so as the universe ages, you get more and more black holes and cue balls. And so in 100 billion years, a large part of the galaxy will be black holes and cue balls and very little gas. And so the number of stars forming will really slow down. And so you may not get very many big stars recycling, and you get more little stars. And so they call this the red cold death of the universe. It sounds very depressing, but it's essentially saying that in any system, you run out of gas and then that's it. And there was actually a talk at the American Astronomical Society talking about the future of the universe. And he was talking about this theories, and that eventually everybody would run out of, the whole universe would run out of gas to make stars. But we're talking about something that happens very, very far in the future, beyond the age of our sun, beyond 10 times the age of our sun, beyond 100 times the age of our sun. So our job right now is to figure out if those models are right, and then also figure out what the future of humanity is in that universe.
Yes. In the chat, we had Angel saying, yeah,
That
that
does sound depressing. It's just a little bit depressing. But it's the same kind of depressing that doctors face, right? The doctors face that, everyone gets older. And we don't like being the fact that everybody gets older, but everybody gets older. And so you just deal with, what do you do with your life, is the fact that you get older. So it doesn't have to be depressing. It's just the way the universe is. And then we deal with how we react to the way the universe is and what you do with our time in it.
Absolutely, Matthew. And I agree with Angel, who says, thankfully, we get to be a part of this universe. Yes. And Matthew, as you were saying, it's how we're spending the time. What are we doing while we are here? And to maybe expound a bit on that, Ivan, I'm very curious to know your experiences with simulations. I know this is really important in astronomical research. Um, could you share a bit about your experiences with simulations and how it relates to the research that you're doing?
Yeah, so the simulation we're doing involves using these model atmospheres and I guess comparing them to the stars that we're analyzing. And we kind of, correct me if I'm wrong about this, but we're adjusting the models and the abundances in them just to try and match the stars that we're looking at. So we're using this model atmosphere to just change it up a bit and get it as accurate as possible. And just seeing how the chemicals in these atmospheres, or in the atmosphere that we have chosen, seeing how the chemicals like bond with each other and just relate to each other. Like if one of them goes up, does another one go down or also go up? Just seeing how they relate to each other.
Yeah, the star is sort of like an ecosystem. So if you put in a lot more carbon, then it reacts. There's some reaction that occurs, and so different molecules form. So so we have to make a model that simulates that ecosystem. And I've always thought that modeling is fantastic. If you can model the climate change on the earth, that's such a complicated system that you start off with such a very primitive model, and you're like try to make a prediction, and you're like, well, this isn't a very good prediction, but I'll predict out 2 years and see what the prediction is. And then you make a more fancy model and you're like, oh, my 2-year prediction works pretty well, maybe I can make predictions of 10 years. And then you add more and more physics or more and more interactions, and you make better models, and you can make longer and longer predictions.
Incredible, incredible. In these last, we have about 15 minutes left. I would be very curious to know, is there any way you can maybe show us some of the screens you're seeing with the weather data? I know earlier when we first started, yeah, we're not having the best weather there where you are. What can we see, Matthew and Ivan?
Well, I would say based on that picture, we can't see much.
Yep, Ivan's exactly right. So there's humidity is still 99% or 100%, and the precipitation is still fog. So that's not great. And then we have the cameras. Here's a camera that looks out a little telescope. This is a telescope called the Automated Planet Finder. And as you might guess, it tries to find planets going around other stars. And you can sort of see the background is all just white. It's just a kind of a foggy night. And this is the image that we were looking at earlier that had the strange white UFO hiding up here, which I didn't know what it was, and now it is gone. It was probably somebody's headlight, or maybe they opened a window inside the building and let out light. But we don't like letting out light from the building. But maybe he walked outside and left the door open as he was checking the weather. I am observing from my office in my house. And Ivan, you're in your apartment, is that right?
Yeah.
So we are remotely connecting to the telescope, but we do have a professional technician who is running the telescope, and they are on a different Zoom call, so they're not connected to this Zoom call, but they are technicians who live on the mountain, and they set up the telescope during the day, make sure the instrument is changed. They're not PhD astronomers. They're technicians. They're people who work at an observatory doing observatory jobs. They have skills like computer support and wiring and soldering, and they know how to work on cars. They're very technical oriented people, but they get to work on these cool instruments, gigantic telescopes which are trying to find planets around other stars. So they work on cool stuff, but in a way that is different than a PhD astronomer might. So they are the ones who are at the telescope, and I would say, hey, let's open the telescope and observe this star. And they're like, it's foggy, it's rainy, it'll damage the telescope. So they're the voice of reason there to protect the telescope, but help me try to collect data.
Amazing. I had the pleasure of visiting Lick Observatory. This is early, maybe October. So some months ago, October, with our factory director, my colleague and boss. He doesn't like that. But Raja Guhadakartha, who of course has used Lick Observatory many times. Is the just stepped down recently as the chair of the Astronomy and Astrophysics Department at UC Santa Cruz, and I'm absolutely pleased to have him as our guide and as our faculty sponsor for Shadow of the Scientist, which is an initiative under the KAST, the Creating Equity in STEM umbrella of programs. And so Matthew and Ivan, even though maybe perhaps it's not possible for students to be, or anyone to be in the control room at this time when you all are observing, they get to join virtually, right? To actually see all the science coming in. Are tours available? Do you have an opportunity for students, for the community to come in, ask questions, maybe get a tour of the control room and of the telescope itself to really see the science, the impact of the science that you all are doing? Because you've done, Lick Observatory is certainly a historically important telescope in the history of astronomy overall in the entire world. Is there access for the public in general?
So the telescope is the observatory is open to visitors for them to do a walking tour, and they can go into the visitor gallery of the telescope we'll be using tonight, the 3-meter telescope. So there's a gallery that they can enter in, and that's open every day of the year. So if you just go up on a beautiful day and want to go for a drive with the family, there will be things to see up there. And if you go on some weekends, most weekends on Saturday and Sundays, they will have the main building there which holds the historic telescopes. And it has a little museum and a gift shop there. So those are open some days. And so you should check the website to see which days and which times they're open. But that's another way. And then during the summer, they have special weekends where they do walking tours. And you can buy a ticket to have a guide walk you around the mountain and point out different telescopes and the science they do and some of the history of the observatory. And there was a school up there. And what was it like to be a kid in the 1920s to go to school on top of a mountain at an observatory? So they have a lot of these interesting, exciting stories. So yeah, there's a lot that can be done, and because you students are local, it's a place that you can go and take advantage of. Jamika, could you tell us, we only have a little bit of time left, and I would love for you to share other things that one can do through Shadow the Scientist.
Oh, I'm so happy to share that, Matthew. Thank you. Yes. Well, we are so thankful to be able to collaborate with astronomers, scientists of your caliber, Matthew and Ivan. It is only through your collaboration and your passion and willingness to share to open essentially the virtual astronomy doors to allow us to come in and shadow your work. And so, what else can you experience through the Shadow the Scientist initiative? Well, of course, astronomy is our foundation. Again, Raja Guhatakartha is a professor at UCSC, University of California, Santa Cruz, in astronomy and astrophysics department. And realized that at the beginning of COVID, when it was no longer possible to kind of be in these places because we needed to socially distance, because it wasn't able, there was not the ability to be there in person. Things moved to Zoom, and because of that, Raja realized that this is an amazing opportunity to share with the public what astronomers do and to give them actual insights into the field, and to honestly demystify what it is that astronomers do. There's no looking through the eyepiece of a telescope. No, these telescopes at observatories are absolutely huge and humongous, and that would certainly fry our eyeballs. We don't want to do that. We don't want to do that. So it's been absolutely incredible. But I'm very thankful and pleased to say that with the collaboration of many others who are also passionate about sharing their science and connecting to the community, we've moved beyond astronomy. I guess on Friday I had our first session with our first oceanography session. So we were with the crew of the Joydes Resolution as they crossed the Strait of Gibraltar. And we had the opportunity to speak to several micropaleontologists about their work and analyzing the cores that are drilled from beneath the ocean floor. And in fact, and next weekend we'll have 2 more sessions, thanks to our onboard outreach officer, Aaron, with the crew to talk to more of their scientists about the work that they're doing, and we'll actually get to see some of the coring happening live. We've also, if you're interested in ecology, here we have partnered with the Lico Na Polina, our research team, who are doing tropical forest ecology, to better understand the impact that we have on our surroundings, but especially with invasive and non-invasive species, and how to really create a more stable environment there. Also, we've been so grateful to work with Mo. Mo of the UCSC Genomics Institute. We had the pleasure of visiting them a few months ago as well. And we've had one session with them in collaboration with Berkeley City College. And I'm looking forward to having more of those sessions. Yes. And we have some more also coming up in neurology and other areas, and of course, astronomy in general from many different places, not just optical, but of course, infrared with Gemini Observatory, which I'm so grateful for. Keck Observatory with the deputy director there, Dr. John O'Meara, as well as with Las Cumbres Observatory, robotic telescopes. And for us, our connection there, in addition to the director, Lisa Strombardi, Dr. JD Armstrong, who was a member of the Institute for Astronomy in on Maui, has the opportunity to work with Las Cumbres Observatory, and we have been doing some asteroid tracking and characterization with JD. So we have many things to offer, and we are always looking for other scientists to collaborate with, to share their science, not only with a specific community, but beyond that, to reach the world, because science truly is a collaborative endeavor. It reaches beyond borders. It reaches beyond so many of the things that can hold us back. And this is part of the reason why I'm so very grateful to be able to serve in this position as the coordinator of Shadow the Scientist, because it raises my awareness and gives me hope and the ability of humanity to see beyond our differences and work together for the betterment of all humans.
So I see that Angel had said molecular biology would be really interesting. So
Okay, Angel, yes. I have a meeting. I need to schedule that meeting with Mo. His name is Mo Mustaki, at the University of California, Santa Cruz Genomics Institute. I had a personal tour there late October, early November. It was wonderful to meet Mo, Samira, and Drew, as well as the others there in the Genomics Institute who were so thrilled to share their science. If you check out our YouTube channel, you can see our first session with Mo. But I'm looking forward to working with them to schedule new ones. And just check back on our webpage. I'll drop that link in the chat to see when that's happening. So that you can be in the front row, virtually front row, to ask those questions. Yes, absolutely, absolutely. Thank you. Yes, Angel. It's my pleasure. Um, and yes, and so I see your question now. If you had another type of scientist, Matthew, that you asked, would you like to see talk through Shadow the Scientist, marine biology, ecology, archaeology? Thank you for that question, because we really appreciate that feedback. And for me, I'm a lover of science in general. And even though astronomy is my first passion, I moved to Hawaii, to the Big Island, to study astronomy, to work in this field. I'm so grateful that in this role as the coordinator of Shadow the Scientist, I am privileged to be able to work with and talk to scientists across all fields of science. It's something that I never thought I could do, Angel, and it's just been so amazing, so inspiring. And of course, I'm learning so much. I didn't even know a micropaleontologist even existed until I was talking with these people Friday on the Jordan's resolution. So we'll have several more coming up with them, and we're looking to expand to other areas of science too. Yes, Angel, it was like I'm still editing. I'm still editing the video, the original recording, but I hope to have that up in the next few days. Angel, it really was amazing. They used words and phrases that I I never even heard of. I had to ask questions about that. And that's what I love. You have Ivan and Matthew here, scientists who are willing to not only share their time, but their expertise and their knowledge, so that others who are interested in these fields can feel welcomed and really bring down that barrier for participation through reaching out and sharing their knowledge and their understanding so that you can feel much more comfortable and confident as you start to work in this field as well. And so I'm absolutely grateful for both of you, Ivan and Matthew. And I'm so glad, Jennifer, Angel, and Metzley, to see you all here today. And so, we're 1 minute past our end time, but it maybe in the next few minutes, if Matthew and Ivan can spare a few more minutes, we would love to open the floor to your questions. Jennifer, Angel, if you have more questions, and Metzley, questions or comments for Matthew and Ivan? And I think it would be okay to just unmute yourself if you'd like to do that, since we are a small, cozy group here. Yes, Angel.
Thank you.
Yes, Matthew. Yes, please, please.
I was just going to say thank you. It is a privilege to be an astronomer. Not everybody gets to work with what they're passionate about, and everybody should aspire to try to work with what they're passionate about. And that's part of what this process is to expose you to a bunch of different things and see what you might find exciting. And the same is true for um, Ivan doing undergraduate research. He might decide that stellar spectroscopy is all sort of interesting, but really planets and doing, spectra of planets is where it's at. Or maybe it's computer programming. Maybe we scare him away and he goes back to computer programming. So.
Yeah, I also want to say thank you because I feel like I have a kind of a good perspective from, I guess, from someone that's looking outside. Since I'm just getting started here, it's just really interesting to learn more every time I work on this project and just work with Matthew in general.
And Ivan, you did a great job with the presentation. A first presentation can be really hard, and doing it for more than an hour, that's spectacular.
I absolutely have to agree, Iván. Yeah, muy bien hecho, muy bien hecho. Qué bueno. Exactamente. Yes, aplauso, aplauso. And we have another comment from Angel. Angel says, I think your work is so amazing and y'all must be so proud. Are you proud, Ivan and Matthew? You feeling good about what
You
you're doing?
bet.
Yeah.
Good. Absolutely amazing. You should. Should. Yes, yes, Angel, exacto. And Angel continues to say, this has been so insightful, and I learned new things, and it's so great to hear straight from the source. Thank you so much for that, Angel. We appreciate that. I agree. It is such a privilege and an honor to be able to spend some time with these astronomers as they are working during the evening. And Angel continues to say, wish good luck to Ivan. And thank you so much for letting us be here. Yes, 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 Ivan, Matthew. Thank you so much for allowing us to shadow you all as you are doing your research into the universe. When can we follow up with you? When can Angel, Jennifer, and Metzley expect to be able to connect again, Matthew and Ivan?
Well, we have more time on the telescope, and so in the spring we might do some more of these Shadow the Scientist work, and then Ivan will be working on his senior thesis, and so we'll have to see where he presents that. and maybe we'll see what that looks like.
Yeah. Mhm. And hopefully we have better weather conditions.
Yes, in the future. Yeah.
I also I hope so too, Yvonne. I hope so too. But what this is the thing about live research, live stargazing with actual astronomers. This is something that you all have to deal with whenever you are on the telescope. So this is authentic, uncurated experience here when we are weathered out. And that's okay. So and like maybe the last 30 seconds, Iban and Matthew, what's the rest of your evening gonna look like?
It's going to be very slow for me because I'm going to watch the humidity sit there. And so I will probably spend some time looking at the data from the previous runs that we've collected and try to get it organized for Yvonne. And Yvonne, what's the rest of your evening looking like?
Well, immediately after this, I'm gonna call my mom because I was supposed to do that earlier today. But other than that, I think I have a few chapters to read for homework. Other than that, go to
Still
bed.
homework as an undergraduate. That's right.
Absolutely, absolutely. Constant learning as a student. And I'd imagine just even as a PhD astronomer, there's always new information, new science that's coming out, and you have to stay on top of that. And I'd imagine that that's something that you do regularly. Well, thank you so much, Matthew and Yvonne, for allowing us to shadow you this evening. We're so grateful to have had you with us this evening. Angel, Jennifer, and Mesley, thank you so much. I will be sending a follow-up survey to you this week for your feedback. We certainly appreciate that. And Matthew and Yvonne, I look forward to connecting with you all again as you host the La Noche community in for observing. And hopefully we'll have some good weather and we can actually see the night sky.
Yeah. Okay. Bye-bye.
Thank you. Aloha.